All right, the third problem is 2008 E2, and I like this one a lot because it combines several different concepts into one problem that's only got two parts to it, A and B. And in just those two parts, you're asked to think about series and parallel resistor circuits, you're asked to think about inductors, and about capacitors. And the second part of the problem is just simply graphing these three currents depending on what's connected across A and B, which I think involves putting a lot of effort into thinking about what's going on here behavior wise and just making a sketch that includes a whole bunch of tricky concepts. So the first one's pretty straightforward. All you're being asked to do is imagine there's a 50 ohm resistor connected between A and B. So you've got one, two, three, four resistors in a combination circuit. You can think of R3 and this thing as being in series, find the equivalent resistance, make your way back into getting the potential drop across R2. So this one's pretty straightforward. I made a mistake on this diagram. Sorry about that. The equivalent resistance for this entire piece of the circuit turns out to be 100 ohms. When you put that 100 ohm resistor in series with R1, you get an equivalent resistance of 300 ohms for the entire circuit. So the entire current is 5 amps. If that's the case, then the voltage drop across R1 is going to be 5 amps times 200 ohms, which is 1,000 volts. And that leaves for this entire parallel branch 500 volts. In the second part of question A, you're being asked to imagine that there is a 40 millihenry inductor in between A and B. And as we've discussed before, the inductor, when the switch is first closed, is going to oppose any current going through that branch. Finally, in part three of question A, you're being asked to imagine a capacitor being placed across A and B, and in an opposite behavior from how the inductor behaves, the capacitor behaves like a wire. That means that you again have to treat R2 and R3 as being in parallel, find that equivalent resistance, add it to R1 to get the overall resistance, and use the usual methods like we did over here. Part B is simply to graph all three of these different currents as a function of time on the same axes, which I really like because you have to think about how they all relate to each other. The easiest one, of course, is the resistor circuit because this current never changes. It remains at 5 amps all the way throughout. For the inductor, you've got an equivalent resistance of 500 ohms in the beginning, and that gives you an initial current of 3 amps. However, as the inductor starts to allow current to flow through it, it's essentially going to eventually allow R2 and R3 to be thought of as just a parallel circuit like it is in this problem. That means that for the inductor, the current will begin at this value of 3.0 amps, but as the inductor starts to come on and include R3 in the circuit, the current will approach 5.45 amps. Finally, with the capacitor, when that thing is first connected in the circuit and the switch is closed, R3 is behaving normally because this might as well be a piece of wire as far as the rest of the circuit is concerned. However, as the capacitor begins to charge up, then this entire branch of the circuit starts to get removed, and so you're left with R1 and R2 in series, and that has an equivalent resistance of 500 ohms, just like this one had in the beginning. So there it is, a really nice problem that allows you to think and calculate some pretty interesting things in a fairly quick kind of way. So capacitors, resistors, and inductors can all be combined into one 15-minute problem.